So imagine you have a cup of water in your hand and you dump it out on the table in front of you. What happens? The water splashes, it flows off the table and makes a big mess. Now you take the same cup of water and you're using your finger, you take it drop by drop and put it on the desk. Now something completely different happens. Instead of flowing off the edges, it just kind of sits in little droplets. Why is that? Why this change in behavior? It's the same water, it's the same table, same cup. All that's changed is the amount of water that you've put down. The size of the water matters, and small things in general don't necessarily behave the same way that large things do. So why is this? Why do drops like to huddle in and pull themselves close? As it turns out, water on a tabletop behaves a lot like penguins do in Antarctica. Penguins like to huddle together for warmth, which is fine if you're the lucky guy in the middle. Yes! You're warm, you're comfortable, you're surrounded by friends and family, but if you're one of the poor guys on the outside, you're literally freezing your tail off. So what these guys want to do is they're constantly pushing to try and get to the inside where it's nice and warm. And what that means is that it's compressing the huddle as a whole. But because they're constantly moving, the huddle also changes shape. Sometimes it merges with another nearby huddle, sometimes it splits, sometimes it grows, sometimes it just changes shape in general. But it's all because nobody wants to be on the outside. That's true of water droplets on a tabletop, that's true of penguins in Antarctica, that's true of high school dances, and it's true of nuclear fuels. So nuclear fuels might look strong and solid and smooth when you look at it normally, but if you take it under a microscope, you actually see that it's made up of little grains that are just kind of stuck together, kind of like a sandcastle. And what happens is that just like the penguins don't want to be on the outside of the huddle, the atoms on the grain surface don't want to be there either. So during irradiation and at temperature, these grains start to grow, some shrink, some change shape. But it's all driven by the simple rule that nothing wants to be on the outside. And by knowing this and understanding this, we can model it and we can predict it. Now if you look closer at one of these grains, you'll see that it looks a little bit wet. What that is gas that's been generated inside your grains during irradiation that's made its way to the outside and kind of popped out as little bubbles that kind of looks like rain on your windshield during a rainstorm. Now, that's not an accident that it behaves that way because, again, the bubbles in this case are behaving like water droplets. Nothing wants to be on the outside, and in knowing this, we can model it and predict it. Now, these changes in microstructure changes the way that heat flows throughout your fuel, as well as fission gas is released during irradiation. But the bottom line is this. The fuel that you put into your reactor is not what you have during operation. It's changed and it's evolved. But by understanding these simple rules, we can predict it and we can account for that for the sake of performance and safety.